In the last video, we defined acceleration, and I asserted that the main reason we care about acceleration is because forces tend to affect the acceleration of an object. And although it's not universally the case, there are many situations where the way the forces will interact on an object will ensure that its acceleration is a constant. So it's worth taking a look at the special case of constant acceleration. And this can get to be a little more subtle than you might think to realize whether or not you're in that special case. But as we work through some problems in the next few videos, we'll touch on some of those subtleties. But for now, if your acceleration isn't constant, hopefully you can at least break it into pieces that are, and then you can use the final part from one piece as the initial values to the next piece and so forth. Otherwise, that's beyond the scope of this series, and you would have to use the methods of calculus to take it any further. So with that aside, the big caveat here is that we are assuming the acceleration is a constant. So if we look at that, we can first start thinking about plotting a typical velocity time graph for constant acceleration. We know if the acceleration is a constant, or actually let's do an acceleration time graph. No, let's do a velocity time graph, sorry. We do a velocity time graph for the acceleration, right? It's going to look something like that. So, velocity time. All right. Well, let's check that through. Remember, our definition of acceleration said that's the change in the velocity with respect to time. Now, as we're going ahead and doing these things, we're going to tacitly assume that our initial time, t0, is equal to 0. If it isn't, it's not the end of the world. Usually what you can do is just rejigger your time coordinates to make the initial time 0. And I'd say 99.44% of the time it is. So with that assumption in place, the acceleration is the time rate change the velocity. This would be the final velocity minus the initial velocity v0 over the final time t minus the initial time, which, well, t0, but we'll just set t0 equal to 0 to make things a little easier. Okay, so now we can just do a little bit of algebra for a moment here. If I multiply both sides of this through by t, I'm going to get v minus v0 is equal to at. And then finally, I'm going to get that v is equal to v0 plus at. So what this is telling me is the final velocity is the initial velocity plus the acceleration times the time. So this is the first of my gang of 4 kinematics equations. Okay. So now I'll go ahead and work on getting the third one. For the third one, what we can do is we can go and say, well, how far did we travel over that time, or over some time t? So let's just drop that down to make it a little clearer. So this is my final time t. And we recall that the displacement is equal to the area under the curve. Okay. So with that, we can say that our initial velocity here is v0, and our final velocity is v, keeping with our convention. And we can remember that the displacement here, we said it was equal to the area under the curve. And this geometric object here is a trapezoid. So if you remember your geometry really awesomely well, you'll remember that that is 1/2 the base. I'll just stick my base here is t. I'll stick that over to the side, times the sum of the two heights. So v0 plus v, like that. And so another way you can think about it is it's the average height here, so the average velocity times the time. And this is a case where the average velocity actually is the average of the two endpoints. So let me just, to help clarify that, oops, that should just be v bar there. To help clarify that, the idea is that this area here is exactly equal to that missing area there, so I could just go and fit it in there. And you can only do this because the velocity is changing uniformly, so it looks like a straight line in a velocity time graph. So you can flip the triangle on the right side of the midpoint over to fit into the left side. So this really is just saying it's the average velocity times the time, but we're being fussily careful about that. Just make sure we're all good on that. All right, so then we can also remember that the change in position would have to be the final position minus the initial position, and we're almost done. So if I just add the initial position to both sides, what I get is that the final position is equal to the initial position plus 1/2 v0 plus vt. This turns out this is going to be the third of my gang of 4 kinematics equations. To get the remaining 2, for what we'll do is for one of them, we can take what we got for the velocity here, and we can stick it into there, and that will give us another relationship. So let's go ahead and do that. This will give us the second of our kinematics equations. So we'll be writing x is equal to x, to x0 plus 1/2 v0. And now we're going to put in what v is, and we'll have another v0 sitting here. So plus v0 plus a t times t. Okay, so therethere's a bit to unpack there, so let's just do it carefully. This is going to be 1/2 plus, x0 plus 1/2 times, well, that'll be 2v0 when I add those two together, plus at. All right. And then we can times the t inside. So this will give us x0 plus 1/2 times 2v0 t plus at squared. And then what I can finally do is I can times the 1/2 through everything. So x will equal x0 plus, okay, 1/2 times 2 is just 1. So we're left with v0 t plus 1/2 times this, so 1/2 a t squared. That's the second of my gang of 4. I'll be summarizing these in a moment. The final one that you get is if we go ahead and, here, let me do a different color to make it a little clearer what I'm doing. For the last one, instead of plugging in v into this, what we'll do is we'll solve this one for t, and then we'll take that solution for t and we'll stick it in there. So let's go ahead and work through that. So starting with our v equals v naught plus at, I can kind of take this backwards and say, all right, at is v minus v naught. So then finally t is v minus v naught over a. And now that we've got that expression for t, I'm going to put it into here. So what we had there is x equals x naught plus 1/2 v naught plus v. And now I'll be putting in my expression for t, and I'll just be careful about it, v minus v naught over a. All right. And just to get things a little more clear, I'm going to commute these two here. So it'll be x naught plus 1/2 v plus v naught, v minus v naught over a. Alrighty, so let's just start by subtracting x naught from both sides. So x minus x naught is 1/2 v minus v plus v naught times v minus v naught over a. And then let's times it through by 2 and a. So this will give me 2a x minus x naught is equal to v plus v naught times v minus v naught. Now if you remember from your algebra, if you've got two binomials that only differ by one of them having a plus sign and the other having a minus sign, it's the first one squared minus the second one squared. We can just step through that real quick though and just FOIL it out just to be clear. So v times v, that would be v squared, that's first outer, minus v naught, inner plus v naught, or well, plus v naught v, but multiplication commutes. Then finally minus v naught squared when we do the last, and those terms cancel. So we get v squared minus v naught squared equals 2a x minus x naught. Then finally I can add the v naught squared to the other side. I get v squared equals v naught squared plus 2a x minus x naught, or a lot of times people just write that as delta x just to make it a little clearer. In either event, this is the fourth and last of my gang of 4. Now I want you to notice something with these, and so to that end I'm going to rewrite them. So our relations, so I'll make a little table. Here's our relation. And then I'm going to write missing over here. I think we'll see how this works. So I've got v equals v naught plus a t. This equation does not have an x in it anywhere, so we say that that equation is missing x, and I usually refer to it as the missing x equation. Then here we have x equals x naught plus v naught t plus 1/2 a t squared. What's this one missing? It's missing v. v naught is there, sure enough, but v itself, our final velocity, not there. So it's missing v, and I'll usually refer to this equation as the missing v equation as we go along. Then our third member was x equals x naught plus 1/2 v naught plus v t. What's this one missing? Yep, you got a. And then finally, v squared equals v naught squared plus 2a x minus x naught. That one's missing t. And it turns out the fact that each of these equations is missing a variable actually makes it very straightforward to figure out the right relation to use for doing a practical problem. But to that end, I want to take a quick detour and talk about just plain solving physics problems. A mnemonic that I learned back in the day was STAR. The S stands for situation. So here, what you always want to do is you definitely always want to start by drawing a picture. You want to identify what is known. You want to identify what is required. And the picture will usually help a lot in figuring out both of those. Also, you want to figure out if you can make any sort of reasonable assumptions, like some of them might even be assumptions that seem so reasonable that you don't even realize you're making them, like, for instance, I'm on Earth. And also, if you can, try to come up with, sometimes you can just kind of play with the numbers a little bit, and you can come up with some sort of an estimate as to what the final answer may be. And by making that estimate, if it turns out that your result is like, more than a factor of 100 off one way or the other off of your estimate, then you might start go, I'm not so sure I did my math right. Okay. So first, just make sure you understand the situation. Draw a picture, figure out what is known and what's required. Then the next step is tools. So here, you're trying to identify the appropriate physical relation for the problem. Now here, physics is a little different from some other sciences, like, say, biology. This is a really exciting era for biology. Biology is currently undergoing its quantitative revolution, and that happens about once in the history of a science. Biology is now at a point where it is able to start making quantitative descriptions and quantitative predictions of things, rather than being a more descriptive field. Chemistry went through that revolution at the beginning, around the end of the 19th, beginning of the 20th century. And physics went through that revolution, roughly in the 16th century or so. So it's an exciting time. But the thing is that physics has been at this whole describing things with mathematical relations game for a while. And where we're at this point is that we can describe so many physical systems that it's pretty much impossible to just have the equation for the thing anymore. And so we have to just take a step back and take statements about nature that are always true and then apply them to the specific situation. So in other words, try not to be in the habit of digging around and looking for an equation that looks like it has the right letters in it. It might have the right letters in it, but if it's not looking at that exact physical system, and they're analyzing some other physical system, then the combination of constants or the exponents or whatever might not be what you need, and you're apt to get the wrong answer that way. So we always try to start with things that are always true. So in this case here, the only tools we've got at the moment are the definitions of the kinematic variables themselves and the gang of four that I've just given you. And I'll give you a cute trick for figuring out how to identify which is which in these kinematics problems. Answer. So here we did some physics for a bit. Here we're going to do some more physics for a bit. This is mostly math. So this is where you're going to take whatever relationship you identified in the tools phase of things, and what you want to do is rearrange it to get what you want on the left-hand side and what you don't, and everything else on the right-hand side. And I'm going to give you a mantra here, and that is letters good, numbers bad. And there's a whole lot of reasons for that, but my general attitude is the only number, with certain exceptions, the only number that's ever worth sticking into a problem right away is 0. Just about anything else, it looks good, it feels comfortable, and it's probably similar to what you've been doing in prior science classes. You need to get out of that habit, and there's several reasons for it. One is it turns out it's easier to find your mistake if you work the problem in letters. And all of us make mistakes when we do this, and it turns out that it's easier to pick out the mistake and fix the mistake if you do it with letters. If you do it with numbers, you just stick all the numbers in, and then if you make a mistake, basically you have no clue where you messed up, and you pretty much just have to start the whole problem all over again, and it becomes super frustrating, and we're all about trying to avoid any more frustration than we have to have here. Also, another issue just has to go to accuracy of things. You would think if you're in the habit of solving things numerically, if you turn the crank and you get a number and then you stick that into the next thing, then you stick that in the next thing, you figure, okay, yeah, I'm rounding on each step, but half the time I'm rounding high and half the time I'm rounding low, right? So what's the diff? Mathematicians have shown that once you start rounding, you'll tend to have all of your round-off errors compound. Sometimes they cancel out, that's fair, but they tend to compound and snowball away. I've had people contact me with, hey, I've done this problem and I've checked the answer and I'm off by a factor of 3 or 4. And it turns out that, yeah, for certain things like trigonometric functions, exponentials, logs, stuff like that, just the accumulated round-off error threw the final answer off by those kind of large factors. And there are plenty of times where being off by a factor of 2 or 3 or 4 is not going to be a good sign. For instance, if you're calculating how much drug a patient should get, that could be a bad thing if you give too much or too little. So by working in letters until the very end, then that means you only have one wave of rounding to do, and then that will minimize things. And when you plug in your numbers, make sure to plug in the units too. And that's because in the last step, review, we're going to look at the answer and see, does it make sense? And the big thing that you always want to do is just make sure, do the units check? If you're expecting the answer to be in meters and you get seconds cubed per meter squared, you probably made a math mistake somewhere. Now, if your units work, that's not a guarantee that you did not make a math mistake. But if your units don't work, that is an absolute guarantee that you made a math mistake. And the other thing you should always check is just plain, is it reasonable? If you've got a problem, for instance, where somebody's throwing a baseball or something like that, and you solve for the final velocity of that baseball, and you get that the final velocity of that baseball is 70% of the speed of light, probably not reasonable. It's probably the case that you made a mistake and that you should probably go back and check your work. So that's the sort of the high level, this is how I tackle any physics problem. So let's do this more specifically for a couple of kinematics problems, just to give some flavor for how this might work. So one problem I can think of is, we could say, having a car. So let me draw a road real quick here. There's the road. We say that the car was traveling 100 meters in 5 seconds. All right, so in that case, I'll go ahead and draw myself a before and an after car. So we can just set the initial position to be 0. Notice here I'm already starting to identify my knowns. And they tell us that it traveled 100 meters. So my final position is 100 meters. Now, I mean, I could have made this 20 meters over here, as long as I made that 120 over there. That wouldn't change the problem at all. But because it wouldn't change the problem at all, let's just make this 0 here. So I've got a 0 to put in, since it's okay to stick zeros in usually. We also are told that the car took 5 seconds to do this. So the change in time is 5 seconds. That will tell me we usually set t initial to 0. In fact, we don't even bother writing it in the equations. So that means t will be 5 seconds when we're over here. Okay, and then this was t equals 0 seconds when we were over there. And we were also told that at the end of this interval, we were going at a 30 meters per second. And since it's at the end of the interval, this would be the final velocity, so it would just be v. And we'd like to know how fast was it going at the beginning of the period. So that's asking for what is the initial velocity. Okay, so here I've identified all of my knowns and unknowns, and I've identified what it is I'm being asked to solve for. And so we can go ahead from the situation here to the tools. So the trick here is, in kinematics problems, is you can identify the missing variables. So let's figure out what's missing here. And by missing, I mean neither asked for nor given. So I go and take a look at this and I realize, hey, I'm missing the acceleration. I'm neither asked for it nor am I given it. So this is great, because if I wasn't given A and I'm not asked to find A, we can save a whole lot of time by not having to solve for A and sticking to something else if we just plain use the relation that doesn't have an A in it. So to that end, my tool is going to be the missing A equation, which says that x equals x naught plus v naught t. Whoops, my bad. I said the missing A equation, didn't I? X equals x naught plus 1/2 v naught plus v t. All right. And like I said, you can go ahead and stick zeros in right away. That's usually okay. All right, so I've identified my tool. Now, I need to rearrange this so that I get the letter that I want, which here is going to be v naught, because that's what I was asked to solve for, on the left-hand side, and everything else on the right-hand side. So now we're into the answer stage, and this is just doing algebra. We're not doing any physics at this particular moment. So we can multiply by 2, so we get 2x equals v naught plus vt. We can divide through by t, so v naught plus v equals 2x over t. Then we can subtract v from both sides and get v naught is 2x over t minus v. All right, now I've got everything on the left-hand side, and they got what I want to solve for on the left-hand side, and I have everything else I want on the right-hand side. So time to begin the review process. I'll stick in the numbers with their units and solve. So this is 2. We were told that our final position was 100 meters, and that this was 5 seconds. And we were told that the final velocity was 30 meters per second. All right, as we're doing this, ask yourself, when you've got more than one term, are the units consistent between terms? If they're not, you might have to either do conversions, or it's possible that you made a math mistake if the physical dimension doesn't check. So let's just check. Meters over seconds, we're good. So whenever you add or subtract two numbers, they always have to have compatible units. All right, so we can do this. 2 times 100 is 200, divided by 5 is 40. So this is going to be 40 minus 30 is 10 meters per second. All right, now let's ask ourselves, is the answer reasonable? Yeah, it's slower than, we were told the car was speeding up. It's slower than what we had before, so that seems very reasonable. And the units check. And so we can feel quite confident that we've probably done this one right. And so we get that initially the car was going at 10 meters per second to the right. All right, let's do one more example here. Again, it'll be a car. So here we're going to have a car hit the brakes. So initially, the car is going at 100 meters per second. Yeah, I know that's race car kind of speeds, but hey, race cars are fine. And we're going to end up at 40 meters per second as my final speed, my final velocity. And we're going to do this over 100 meters. All right, so if this distance here is 100 meters, once again, I am free to decree that x naught is equal to 0 just to make my life easier, which makes that final position 100 meters. And I want to know what is the acceleration. Alrighty. Well, first off, just given the kind of numbers, we're talking race car speeds and race car distances, so I'm expecting a race car-like thing. And I know that, for instance, Formula 1 cars, when they hit the brakes, they can generate several G's, several times the acceleration of something just falling all by itself, which in just a second we'll get to is 9.8 meters per second per second. And so I'm expecting something, a few times that. The other thing I know is that the initial velocity is bigger than the final. That means the velocity is decreasing. So this means that the acceleration vector, even though I don't know what it is, I've already worked out the direction that's pointing to the left. So this tells me whatever my final answer is, it better be negative, or else I made a math mistake somewhere. All right, so that's my situation. Let's work the tools. Again, the idea will be to identify the missing variable. So again, that's the one that's neither asked for nor given. A is given, so, or sorry, A is asked for, so that's not missing. I got V naught, V, X, X. Okay, I'm missing T. I'm neither asked for nor given the time. So the relation I want to use is going to be V squared equals V naught squared plus 2A X minus X naught. All right. And once again, because I set X naught to be 0, I can make my life a little easier by just plain making that 0, right? And let's go ahead and start turning the crank to get the acceleration. So first I can subtract V naught squared from both sides equals 2AX, and I need to get A by itself, so A will be V squared minus V naught squared over 2X. All right, we'll put in the numbers now, and so we know that the final velocity was 40 meters per second squared minus the initial velocity was 100 meters per second squared over 2 times 100 meters. Okay, so now we're getting into the review phase here as we turn the crank. All right, if you punch the numbers into your calculator, you're going to get negative 42, and we need to work through the units here. So here, whenever you square a number, you have to square the units too. So let's just follow that through, make sure we're good. So this is meters squared over seconds squared. That's meters squared over seconds squared. So in the numerator, we have compatible units. So the units of the numerator are meters squared over seconds squared. I then divide by meters, and sure enough, meter per second squared, that is the unit of acceleration. So the units check. Based on what I knew about race cars, this also makes sense. And since I wrote the problem and I am that hopeless of a nerd, yes, I did engineer it so that we would have a reference to the answer to the ultimate question of life, the universe, and everything from The Hitchhiker's Guide to the Galaxy by the late Douglas Adams. Definitely worth a read if you've never read it. At least I found it hilarious as a young nerdling. Alrighty. And since I mentioned acceleration due to gravity, let me just take a quick moment here and talk about that. So, mostly so they can give you more problems. A lot of textbooks will quote that if the only force acting is gravity, and we haven't formally identified forces yet, but if the only but we can do this intuitively. If the only force is gravity, then the acceleration, and here this would be vertical, would be downward at 9.8 meters per second squared. Now, what they will do is they'll often say that this is equal to negative g, and I really wish that authors would lay off of that. G, technically speaking, is not an acceleration. It's what's called a gravitational field strength. The units of a gravitational field strength are actually newtons per kilogram, and we haven't worked out what a newton is yet, but I will assure you newtons per kilogram are dimensionally compatible to meters per second squared. So the units do check out that way. I am not a fan of doing free fall problems and sticking the symbol G into things. I prefer, if you have a free fall situation, that you just write A. And free fall is trickier because all it means is that the only force is gravity. It doesn't necessarily mean the object's falling down at the moment. You could have thrown it up, and after it's left your hand, assuming that it's a really slippery, it's a really aerodynamic object, so we don't have to worry about air resistance. then the instant it leaves your hand, it'll be accelerating downward. And remember, the minus sign here in the context of being vertical means down. It'll be accelerating downward at 9.8 meters per second squared. So first, what that means is the velocity upward will be positive, but decreasing. And then eventually we'll flip sign and start heading downward. And then at that point, the velocity and the acceleration vector arrows will be pointing in the same direction. They'll be parallel, which means that we'll then be going down and picking up speed. So to a physicist, the term free fall means that the only force is gravity. As a practical issue, unless you're at very high altitudes, air resistance is a thing. We tend to ignore it a lot in introductory treatments for the expedient reason that if you try to throw air resistance into the model things, the math is absolutely horrendous. And so it makes it very hard to follow through. In fact, it's beyond, again, it requires lots of calculus to do. And it often turns out that if you're just trying to get decent numbers, a lot of times you can wish air resistance away, or you can figure out how to correct for air resistance after the fact. So it's not necessarily the end of the world that we are neglecting air resistance. It's not that air resistance is negligible in nature. It absolutely is not. It's just that we have to start somewhere, and if we start with air resistance off, we can get somewhere. Later, if we need to really worry about it, we can go back and worry about air resistance at that point. Alrighty, so that's what I've got there. I will catch you in the next one.